Hello everyone and welcome back to the class. In today's class we will discuss about the capacitors. So let's see what is the capacitor everyone. Capacitor are devices that store large amount of energy in the form of electric field. So what capacitor is doing? It is storing large amount of energy in the form of electric field. They can act as an instantaneous source of energy for very short interval of time. So exactly what capacitor is doing? It is storing large amount of energy in the form of electric field, and when we have required this energy, then this capacitor is releasing this energy in very short interval of time. Now the next thing is how it is appearing, correct? So if we will open any electronic devices like laptop, tablet, mobile phone or TV, so in this electronic circuit, these capacitors are present, correct? So it is looking like this everyone. Here we have uh, two terminal. One we will connect with the positive terminal of the battery and the second end we will connect with the negative terminal of the battery. So when we will connect this capacitor with the battery, then it will get charged, correct? And on the capacitor, voltage is also written and capacitance is also written. This microfarad is what? It is a unit everyone. Unit of capacitance. So about this we will discuss, don't worry. Alright, so microfarad is what? It is a unit. Okay. Now the next thing is where we are using this capacitor everyone, where we are using. So we know that it is present in the electronic devices, in the mobile phone, in the camera, correct? In the fan also it is present, correct? But why it is necessary for us here? See it in the flashlight, you can see it in the camera, we have flashlight, correct? So when we will click on the camera, then we have required large amount of energy for this flashlight, and this large amount of energy who's providing here one capacitor is connected inside this capacitor, so it is storing large amount of energy and we have required this large amount of energy for short interval of time. So that's why here we are using capacitor, correct? And the second application is here in the fan. In the fan also we are using capacitor, correct? So if you will look your fan everyone, so this type of capacitor is present there. All right, so here one capacitor is present in the fan. In the fan also we have required large amount of energy, correct? So that's why we are using here also capacitor. So this is the uses of this capacitor everyone. All right, note down. Now we will discuss how to make good capacitor. So if you want to make a good capacitor, so it should store energy in the confined region. This thing we knows, correct? A good capacitor stored energy in confined region. So if you want to make a good capacitor, so what we should do? So if I will take two conductor and put at some distance, then it is capacitor everyone. This is capacitor. Here we have two conductor and we are putting this two conductor at some distance, then it is the capacitor. But it is good or not, this thing we have to check. So if I will draw the field lines, so field is perpendicular to the surface, correct? Electric field is always perpendicular to the surface. Correct? So we can see it here field is perpendicular to the surface. So this line, maybe it will bend and it will go from here to here. This thing is possible here. But these lines are wasting everyone. So only energy is storing in this region, correct? And this energy is wastage. That's why it is not a good capacitor. For the good capacitor, it should store energy in the confined region. So if I will take two plates, two parallel plates and put at some distance, now it is good capacitor, because now what is happening, we know that field lines are perpendicular to the surface. Now wastage of electric field is not happening here. If the wastage is not happening, then the energy wastage is also not happening. That's why parallel plate capacitor is the good capacitor. If I will take arbitrary shape and put it at some distance, then it is not a good capacitor. It can be capacitor, but it is not a good capacitor. Alright, so about this we will discuss about this parallel plate capacitor. It is part of our syllabus, and then we will discuss about the cylindrical capacitor also, and we will discuss about the spherical capacitor also. So now this thing we know that if you want to make a capacitor, then we will take two conductor and we will put at some distance. Now capacitor is ready. But for the good capacitor, it should store energy in the confined region. Then it is good capacitor only. Alright. If I will take one single conductor, then it is capacitor or not? Think it, everyone. If suppose I am taking one conductor, then it is behaving as a capacitor or not? Then it is also behaving as a capacitor. Like we have here positive charge on this conductor. So if I will draw the field lines, so this is the field lines, everyone, and this field is going till infinite. So right now it is behaving as a capacitor, but it is not a good capacitor. Why it is not a good capacitor, everyone? Because here what is happening, energy is spread in infinite region, correct? So it is not a good capacitor, but it is capacitor, everyone. So single conductor can also behave as a capacitor. But for the good capacitor, it should store energy in confined region. Keep this thing in your mind. Note down. Let's see next topic, capacitance. So what is the capacitance, everyone? Capacitance is the measurement of the capacitor ability to store an electrical charge. Correct? So what this capacitance is measuring? It is measuring how much capacitor can store electrical charge. It is defined as the ratio of electrical charge stored on the each conductor to the potential difference between them. So if you want to write capacitance of the capacitor, so what we have to do it, we will write charge present on the capacitor and we will divide this charge with the potential difference between the plate, and it is equal to what? It is equal to capacitance. So this is the capacitance, everyone. And no need to think like this, capacitance is directly proportional to charge. Means if I will increase the charge, then capacitance will increase, correct? Capacitance is independent from the charge, everyone. Keep this thing in your mind. Why it is happening? Because if we are increasing capacitance, if we are increasing charge on the plate, then potential difference between the plate will also increase. So if we are increasing charge on the plate, everyone, then what is happening? The potential difference is also increasing here. So we can see it here. C is the ratio of Q by V. Both are increasing and both are present in the ratio. That's why C is constant here. Means it is independent from the charge, everyone. So capacitance is not depending on the charge present on the plate, correct? Capacitance is depending on the physical dimension, correct? What is the separation between the plate and how large plates we have, and what is the medium between the plates. On these parameters, capacitance are depending, everyone. For example, let's suppose here we have parallel plate capacitor, correct? So here we have two plates, and let's suppose distance between the plate is D and the surface area of the plate is A. So it is depending on the surface area of the plate and the separation between the plate, correct? And what is the medium is present between these two plates, correct? On this also it is depending. So it is depending on the area of the plate, separation between the plates and the medium between the plates, but it is not depending on the charge, correct? So keep this thing in your mind, everyone, and you can compare this capacitance with the bucket also, correct? What are the uses of bucket, everyone? Bucket we are using to store the water, correct? If the size of the bucket is large, then the capacity of storing water in the bucket is large, correct? So capacity of the bucket is depending on the dimension. Same thing is happening with the capacitor also. All right. If the size of the capacitor is large, then definitely capacitance of that capacitor is large, everyone. So note down this thing and keep this thing in your mind, everyone. Now let's see next, everyone. Unit of capacitance. So unit of the capacitance is farad, and farad is very large unit, everyone. It is not a small unit, it is very large unit. So generally we are using microfarad, picofarad and nanofarad. These units we are using, correct? Microfarad meaning 10 raised to minus 6 farad. Pico means 10 raised to minus 12 farad. And nano means 10 raised to minus 9 farad. So these units we are using because farad is very big unit, everyone. That's why. So note down this thing is also, everyone. Let's see it next, everyone. Capacitance of an isolated spherical capacitor. So now we want capacitance of isolated spherical capacitor. So let's see it how we can find. So first of all, here we have required one isolated spherical conductor. Alright. And the radius of this conductor is, let's suppose, capital R. And the charge present on this conductor is Q. So what is the potential on the surface of this conductor? It is K Q by R. This thing already we know that. We are finding here capacitance, and capacitance is the ratio of Q by V. So total charge is Q, everyone, and V is KQ by R. Q is cancelling. So capacitance equal to we have R by K. Alright. K is what here? It is the Coulomb constant. K is what? It is the Coulomb constant, and the value of Coulomb constant is what? It is 4 pi epsilon naught. So if I will replace K with 1 upon 4 pi epsilon naught, then finally we are getting capacitance is equal to 4 pi epsilon naught into K. This thing we are getting, everyone. 4 pi epsilon naught K. This is the capacitance, correct? So capacitance for isolated spherical capacitor is 4 pi epsilon naught K. Note down, everyone. Let's see next slide, everyone. Common voltage and redistribution of charges. So what we are doing here we have two conductor. So we have two conductor 1 and conductor 2. Let's suppose radius of the first conductor is R1 and the radius of second conductor is R2. And let's suppose charge present on the first conductor is Q1 and on the second conductor is Q2. So what we are doing here, everyone, initially charges Q1 and Q2. We are connecting this both conductor with one wire. And we are assuming, let's suppose potential of first conductor is greater as compared to second. So if the potential of the first conductor is greater, then what will happen? Charge will flow from higher to lower potential. This thing we know, correct? So slowly charge is flowing. It is similar as a heat is flowing from higher to lower temperature. This thing we know from the 11th class, correct? Heat is always flowing from higher to lower temperature. So here what is happening? Here charge is flowing from higher to lower. So slowly charge is flowing. After some time what will happen? The potential of this both the sphere is becoming equal, correct? So potential will become equal, everyone, after some time, and that common voltage we want here, correct? This thing we want. So let's see how we will get this common voltage. See it, everyone. Let's suppose capacitance of this first conductor is C1 and second is C2. All right. And the potential initial is V1 and after then V2, and after connecting the wire, common voltage is V. All right. So before connecting, what is the total charge? It is Q equal to Q1 plus Q2. Q1 is what? It is the initial charge on this first conductor. Q2 is the charge present on the second conductor. So total charge is the summation of Q1 plus Q2. And let's suppose after connecting the wire, here redistribution of charges is happening and the Q1 dash charge present on the first conductor and Q2 dash charge on the second conductor, everyone. This is the final charge after redistribution. But charge is conserved. So if I will add this both, so it should be again equal to Q, everyone. So Q1 dash plus Q2 dash should be equal to Q. So here we have two equations. Now equate this both. So if you will equate, then we have Q1 plus Q2 equal to Q1 dash plus Q2 dash. Now what is the Q1? Q1 can be written as C1 V1. Initial potential of the conductor is what? Is the V1. So, and initial charge is Q1. So it is Q equal to CV. So C1 V1. Q2 can be written as C2 V2. What is the Q1 dash, everyone? Q1 dash can be written as C1 V and Q2 dash is C2 V. Why I am using here same potential VV I am using? Because after connecting the wire, potential of both the conductor is same, everyone. That's why we are using V, and this V we want because here we want common voltage. So after simplification, you will get common voltage V value. It is C1 V1 plus C2 V2 divided by C1 plus C2. This thing we will get. This is the common voltage, correct? Now we want one more thing, everyone. We want here final charges. Final charge also we want after redistribution. So final charge on the first conductor is Q by Q R1 by R1 plus R2, correct? And final charge on the second conductor is what? Q R2 by R1 plus R2. How we will get this result, everyone? See it. After connecting the wire, potential is same. So V1 is equal to V2. And V1 can be written as what? K Q1 dash by R1. And V2 can be written as K Q2 dash by R2. Correct? KK is cancelling here. So here we have Q1 dash by R1 equal to Q2 dash by R2. Correct. So here we have two equations, two relations we have. We have this result, everyone, and we have this also. So if we will use this both result and if we will simplify, then we will get these results. Q1 dash is what? It is the final charge present on the first conductor. Q2 dash is what? It is the final charge on the second conductor. Q is what? It is the total charge. R1 is the radius of the first conductor. And R2 is what? It is the radius of the second conductor. So final charge is what, everyone? After simplification, you will get this result. And this result you have to keep in your mind. These results are important. And how you can remember this result? When I am writing Q1 dash, then in the numerator we have R1. When I am writing Q2 dash, then in the numerator we have R2 and other things are same. Here we have Q, here also we have Q, here we have R1 plus R2 and here we have also R1 plus R2. So other things are same, everyone. Only numerator is changing here. So keep this thing in your mind and remember it. Alright, note down, everyone. Then we will discuss one numerical on the basis of this concept. Note down. Let's see one question on the basis of this concept. Two metal spheres of radii 2 cm and 3 cm are given a charges 2 into 10 to minus 2 coulomb and 3 into 10 to minus 2 coulomb. If they are connected by the conducting wire, the final charge on the big sphere. So here we want what is the final charge on the bigger sphere. So let's suppose this is a smaller sphere, radius is R1 and this is R2, radius of the bigger sphere, correct? R1 and R2. This is Q1 and this is Q2. Charge on the first sphere and charge on the second sphere. We want what is the final charge on the bigger sphere. This thing we want. Okay. So let's see it. How we will get final charge on the bigger sphere. It can be written as Q2 dash equal to total charge and multiply R2 divided by R1 plus R2. About this formula already we know, correct? So about this formula we know Q2 dash can be written as Q R2 by R1 plus R2. So this formula we are using here. Okay. So Q2 dash is equal to Q R2 by R1 plus R2. Now what is the value of Q? Q is the total charge. So total charge is how much, everyone? 2 into 10 raised to minus 2. This is Q1. And Q2 is 3 into 10 raised to minus 2. So add this both, then you will get total charge. And it is how much? 2 plus 3. It is 5. 5 into 10 raised to minus 2 coulomb. This is the total charge. So 5 into 10 raised to minus 2. R2 value is what here? What is the R2 value? It is 3 centimeter. R1 plus R2, it is 5. So here 5 is cancelling. Then finally we have Q2 dash equal to 3 into 10 raised to minus 2 coulomb. This is the final charge on the bigger sphere, and this is the final answer. So correct answer is option A here. Note down everyone. Let's see next question. 10 raised to 6 small water drops, each of capacitance C, joined to form one large spherical drops. The capacitance of the bigger drop is, so here we want capacitance of bigger drop. So let's see how we can do it this question. In this question we have 10 raised to 6 small drops. Correct. We are combining this all drops and we are making one big drop here. Let's suppose radius of the big drop is capital R and the radius of the small drop is small r, everyone. So what is the capacitance of the small drop? It is 4 pi epsilon naught r. And the capacitance of the bigger drop is what? C dash equal to 4 pi epsilon naught, and the radius is r, so it is 4 pi epsilon naught r. This is the capacitance of the bigger drop, and this thing we want. So we want the capacitance of the bigger drop, so we have required capital R value. Once we will get this capital R value, then easily we will solve this numerical and we will get the answer. So how we will get relation between small r and capital R? Think it everyone, how we can get. We know that volume is conserved, correct? So volume of small drop can be written as 4 by 3 pi r cube. This is the volume of one small drop. Here we have 10 raised to 6 drops. So volume of the 10 raised to 6 drop can be written as 10 raised to 6 into 4 by 3 pi r cube. And this volume should be equal to volume of the bigger drop, 4 by 3 pi r cube. Now this and this will get cancelled out. So here we have 100 r equal to r, everyone. If we will do it root cube on both sides, so we are getting 100 r equal to r. So C dash is equal to what? It is 4 pi epsilon naught, and capital R value we got it 100 r. Correct? And already we have 4 pi epsilon naught r is what? It is C, everyone. So it is 4. We will replace 4 pi epsilon naught small r with the C. So now we have 100 C, everyone. So capacitance of the bigger drop is what? It is 100 C. So the correct answer should be option C. So C is the correct answer for this question. So I hope this thing is clear to everyone. Note down everyone. Let's see it. Next question. Two metal spheres, one of radius r and the other of radius 2r, both have same surface charge density sigma. If they are brought in contact and separated, then the new surface charge density on each of the sphere are respectively. So let's see it how we can do it this question, everyone. Here we have two spheres. First sphere has radius r, second has 2r. Surface charge density is same. So charge on first sphere can be written as sigma 4 pi r square, and charge on second sphere can be written as sigma 4 pi, and the radius is 2r. So how much it is? Q2 equal to 16 sigma pi r square. So charge present, initial charge present on the first sphere is 4 sigma pi r square, and it is 16 sigma pi r square. So what is the total charge here? Total charge is Q1 plus Q2, means it is 20 sigma pi r square. This is the total charge on both the sphere. Now we are making contact between these two spheres. So here redistribution of charge occurs. So Q1 dash final charge on the first sphere after the separation is Q1 dash equal to, correct? So we are making contact and then we are separating. So after the separation, Q1 dash is how much, everyone? It is total charge. This formula we know already. Q1 dash can be written as total charge R1 divided by R1 plus R2. This formula we know, correct? So we will put here value. So Q1 dash is equal to Q equal to 20 sigma pi r square. R1 is R, R2 is 2R, so it is 3R. We will add this both. R is cancelling. So what we are getting, Q1 dash we are getting 20 by 3 sigma pi r square. All right. Now, what is the Q2 dash, everyone? So Q2 dash equal to final charge, total charge R2 divided by R1 plus R2. This formula also we know, correct? So from here we will get Q2 dash is equal to Q. Total charge is how much, everyone? It is 20 sigma pi R square. What is the value of R2? What is the value of R2? It is 2R. So 2R by 3R. So this is 3R. Okay. Now RR is cancelling. Then we have Q2 dash equal to 40 sigma pi R square divided by 3. This thing we have. So final charge after the separation we got it. Now we want charge density. So sigma 1 can be written as what? It is Q1 dash divided by surface area, which is 4 pi R square. So sigma 1, what is the value of Q1 dash? Q1 dash is 20 sigma pi R square by 3 multiply 4 pi R square. Pi R square is cancelling. This is 4, so this is 5. So finally we are getting sigma 1 is equal to 5 sigma by 3. Correct? So on the first sphere, surface charge density after the separation is how much, everyone? It is 5 sigma by 3. Now see it, sigma 2 Q2 dash divided by surface area, which is 4 pi, and here radius is 2R square of 2R is 4R square, so it is 16 pi R square, correct? So surface area of second sphere is what? It is 16 pi R square. So sigma 2 equal to Q2 dash. Q2 dash is how much? It is 40 sigma pi R square divided by 3 into 16 pi R square. Now pi R square is cancelling, and if we will simplify this, this is 40, this is 16, so this is 10. If we will divide with the 4, and this is 4, so this is 10, this is 4, so this is 5 now, and this is 2 if you will divide with the 2. So finally we are getting 5 sigma by 6. So sigma 2 is equal to what, everyone? It is 5 sigma by 6. So we got it, sigma 1 as well as sigma 2 also. Now check options. So if you will check here option, then which one we are getting? Yes, we are getting option number 4. 5 sigma by 3 and 5 sigma by 6. So the correct answer is option number 4. Note down, everyone. Let's see next slide. Now we will discuss about the types of capacitors. So let's see it. First type, everyone, parallel plate capacitor. So capacitance of parallel plate capacitor can be written as A epsilon naught by D, where A is what? It is the area of the plate. D is what? It is the separation between the plate, correct? Now let's see it how we are getting this formula. So see it, everyone. First of all, take two parallel plates. And put these two plates at D distance. Charge on first plate is plus Q and the charge on the second plate is minus Q. Surface area of the plate is A, everyone, correct? So first of all, what we are doing, we are giving some charge to this capacitor. Then we will find electric field between the plate. So now the next thing is what? Find out electric field between these two plates. So what is the net electric field between these two plates, everyone? Due to the one plate, electric field is sigma by 2 epsilon naught. Due to the second plate, it is sigma by 2 epsilon naught, correct? So net electric field between these two plates is what? It is sigma by 2 epsilon naught. plus sigma by 2 epsilon naught. So how much it is? Sigma by 2 epsilon, sigma by epsilon naught. So if we will add sigma by 2 epsilon naught plus sigma by 2 epsilon naught, then we are getting sigma by epsilon naught. This is the net electric field between these two plates, correct? So this thing we got it. All right. Now the second thing is calculate potential difference between these two plates. So potential difference between these two plates, how we will get? We knows one formula, everyone. V equal to ED. Correct? This formula we knows. From this formula, we will get relation between electric field and potential. All right. Here V is what? It is the potential difference between these two plates, and E is the electric field. All right. Here we have negative sign also, but here we are interested only in the magnitude. Minus sign is representing here, if we will move in the direction of electric field, then potential decreasing. But here we are only interested in the, correct, in the magnitude. That's why no need to worry about the negative sign. So potential difference also we got it. Now the next thing is what here? Let's see next thing. Step 3. We know that Q equal to CV. So from here C equal to what? It is Q by V. Correct? So V already we have, it is ED, and E also we have E also we have, it is sigma by epsilon naught and multiplied D. So this thing we are getting. All right. Okay. And sigma is what? It is the surface charge density. So surface charge density can be written as what everyone think it. It is charge per unit area. Correct? C equal to Q epsilon naught charge per unit area. So A we will write in the numerator by D. So Q is cancelling. Then finally we have C equal to epsilon naught A by D. This thing we are getting finally. And this is the capacitance for parallel plate capacitor. Keep this formula in your mind, everyone. Note down. Let's see it. One question. On the basis of this concept, a parallel plate air capacitor is charged to the potential difference of V volt. After disconnecting the charging battery, the distance between the plates of the capacitor is increased using an insulating handle. As a result, the potential difference between the plates decreases, becomes zero, does not change, increases. So which one is correct? Let's see it how we can do it, this question, everyone. So this is parallel plates capacitor. First of all, connect with the battery. Correct. So now charge is present on this capacitor. So what we want to do it here, we are increasing distance. Separation between these plates we are increasing. And we are using here insulating handle. Correct. For the separation. So we want here potential difference between the plates. So we know that potential difference between the plates can be written as what? Del V equal to ED. Correct. Del V equal to ED, this relation we know that. What about the E here? E is constant. Between the parallel plates, electric field is constant, everyone. Because the formula is what? It is sigma by epsilon naught. Electric field between these two plates is what? It is the sigma by epsilon naught. So sigma is constant and epsilon naught is also constant. Both are constant. So electric field is constant. So we can say that potential difference between the plate is directly proportional to D. Correct? So if we are increasing separation between the plates, so definitely potential difference will increase. Hence, correct answer is option number 4. Increases. Correct? Note down, everyone. Let's see next question. A parallel plate capacitor has capacity of 10 microfarad with a plate separation of 8 centimeter. If the separation is reduced to 2 centimeter, the capacity will increase. So let's see how we can do it this question and what is happening here. Parallel plate capacitor capacitance formula is what? C equal to epsilon naught A by D. Correct? So here separation between the plates we are increasing. So when we are increasing separation, then what will happen? Area will remain same and epsilon naught also not change, correct? So epsilon naught and A both are constant. It is not varying. So we can say that capacitance is inversely proportional to D, correct? Because epsilon naught A both are constant. So here C1 by C2 equal to D2 by D1, correct? Because C is inversely proportional to D here, that's why. So what is the C1? Initially, capacitance of the capacitor is given 10 microfarad, so it is 10. C2 we don't know, so write down as it is. What is the D2? Final separation between the plate is 2 centimeter and initially it is 8 centimeter, correct? So how much C2? It is 40 microfarad. So if the separation is becoming between the plate is 2 centimeter, then capacitance is 40 microfarad. This thing we are getting. Alright. So the correct answer is what? It is option number D, 40 microfarad. Note down everyone. Let's see next topic, force between the plates of parallel plate capacitor. So here we want force between two plates. How much force is acting between two plates? This thing we want. So this is capacitor's plate. And let's suppose on one plate we have plus Q charge, correct? And we are assuming second plate is present in the electric field of the first plate. So this is first plate, correct? And the electric field created by the first plate is this. So this is electric field created by the first plate and the second plate is present in this electric field. This thing we are assuming. So the second plate and second plate present in this electric field, correct? So force on second plate due to the first F21. So it is what it is on this second plate we have negative charge, correct? And on the first plate we have plus charge. So force on the second plate due to the first can be written as what? Charge present on the second plate and the electric field created by the first plate. And due to flat plate, electric field created is what? It is sigma by 2 epsilon naught, correct? And sigma is what? It is the charge density. So it is Q by A. Now put this value here, then we will get, put here sigma value, which is Q by A. So we have finally Q square by 2 epsilon naught. So this is the force on the second plate due to the first F21, correct? And this is the direction of F21. Now we want force on the first plate due to the second. This is how much, everyone? So here, according to Newton's third law, we know this thing, always forces are acting in pair, correct? So always forces acting in pair, this thing we know from the Newton's third law. So force acting on the first plate on the second and force acting by the second plate on the first is same, everyone. Magnitude should be same according to Newton's third law, because these both are action reaction pair. So magnitude is same, but direction is opposite. So F21 is equal to F12. But the direction is opposite. That's why if I will write in the vector form, so F21 is equal to minus F12. This is the direction of F12 force. Correct? So direction is opposite, but the magnitude is same. And this thing we know from the Newton's third law. Forces always acting in pair. Correct? So this both forces are action reaction pair. Note down, everyone. Now let's see one question on the basis of this concept. A parallel plate air capacitor has capacity C, distance of separation between the plate is D, and the potential difference V is applied between the plates. Force of attraction between the plates of parallel plate air capacitor. So here we want force between the plates, correct? So already we know that force between the plates can be written as Q square by 2A epsilon naught. This thing we know, correct? And if we will look these options, so here in the options Q is not given. Here we have C and V. So we knows one thing, Q can be written as CV, correct? So here F equal to, if I will put Q equal to CV, then we have C square V square by 2A epsilon naught. And in the denominator, if you will look, then D is present in the option. So I will multiply with the D and divide with the D. This thing I am doing. And 2 epsilon naught D by 2 epsilon naught by D is what? It is a C. So finally what we have, C square V square divided by 2CD. Now C and 1C is cancelling, so we have CV square by 2D. So finally we have CV square by 2D. This thing we have, correct? So force between plates, how much? It is CV square by 2D. So the correct answer is what? It is option C, CV square by 2D. This is the correct answer. Note down everyone. Now let's see next topic, energy stored inside the parallel plate capacitor. So here we want energy stored between these plates, correct? So energy between plates we have required. So here we have two plates, and let's suppose one plate is fixed and charge present on the first plate is, let's suppose, plus Q, and second plate is present near to the first plate. So this second plate is very close to this first plate, correct? But between these two plates we have little bit separation, correct? So, and on the second plate we have minus Q charge. Now we want to separate this both plates. So here we need to hire one external agent, correct? So we need to hire here external agent. So this external agent apply force in this direction. So work is happening due to this force, correct? So we are hiring one external agent. This external agent is applying force in this direction, correct? And he is doing some work. And whatever work he is doing, that work is storing as a potential energy, correct? So whatever work he is doing, it is storing as a potential energy. But for this, net force should be 0 on this plate. So external force and the force between the plates should be equal. Then only the net force is 0. Correct? So here net force should be 0. So the external force and force between the plates should be same. Should be equal. Correct? Then only net force is 0. If net force is 0, then acceleration is 0. Then change in velocity of this plate is 0. Then only whatever work he is doing, that work is stored as a potential energy. Alright? Okay, so work done by the external agent can be written as what it is, force, and let's suppose separation between the plate is D. So external force into displacement in the direction of external force. We will multiply, correct, this both, and let's see it, what we will get. What is the external force? How much external force is acting on this plate? It is equal to force between the plate, and force between the plate is constant here because the electric field is constant, correct? Between the plate we have constant electric field, so definitely force between the plate is constant, so external force should be also constant, and it is Q square by 2 epsilon naught. Q square by 2A epsilon naught into D. Alright, and we knows one thing, Q equal to what? It is CV, correct? And we knows one more thing, A epsilon naught by D is what? It is C, everyone. So A epsilon naught by D is C. So we have Q square by 2C. We know Q equal to CV, so it can be written C square V square by 2C. I am replacing Q with CV. Now CC is cancelling, so we have half CV square. So work done by the external agent is how much? It is half CV square. So whatever work he is doing, that work is storing as a potential energy. So work done by the external agent is equal to what? It is equal to potential energy, and it is equal to half CV square. All right, half CV square. So this is final answer, everyone. Correct. So energy stored between the plate is how much? It is half CV square. So keep this result in your mind. Note down, everyone. Let's see one question on the basis of this concept. A capacitor is given a charge Q. The distance between the plate of the capacitor is D. One of the plate is fixed and the other plate is moved very slowly till the distance between them become 2D. Find the work done by the external agent. So work done by the external force or external agent we want here. So what is happening here? We have two plates and first plate is fixed, correct? And second plate is present at D distance. Alright, so second plate is present at a D distance. And how much charge is present? Q charge is present on this capacitors, correct? So here we want to move the second plate from D to 2D, correct? So if you want to move the second plate from D to 2D, then how much work external agent has to do? So this is a direction of external force, correct? And here the second plate moving very slowly. So external force and force between the plate is equal, correct? So external force and force between the plate is equal. Then the net force on the plate is 0, correct? Then acceleration is not happening here. So required external work is equal to what? It is the external force into displacement in the direction of external force. So it is 2D minus D, correct? And what is the external force, everyone? What is the external force? External force is equal to force between the plate, and the force between the plate can be written as Q square by 2 epsilon naught. This thing we know. And 2D minus D is what? It is D, everyone. So Q square D by 2 epsilon naught. This is the work done by the external force, and this is the required answer. So correct answer is option A here. Note down, everyone. Now let's see it next, everyone. Energy density of parallel plate capacitors. So now we want energy density, correct? So here we have two plates. And energy between these plates we know already, correct? Separation between the plate is, let's suppose, D, and the area of the plate is A. So energy between these two plates we know it is half CV square. But now we want energy density. So energy density can be written as energy per unit volume, correct? And energy, how much we have? It is half CV square between the plates. And the volume of the capacitor is what? It is the cross section area into D. So it is AD. All right. Now, what is the value of C? We need to simplify this. Let's see what we will get. I'm doing here. So U equal to half C is what? It is epsilon naught A by D, correct? And V is what? It is ED. So it is E square D square divided by AD. All right. Now, here we have D, here we have D. So it is D square, and D square is cancelling, and AA is cancelling. So finally we have energy density is equal to half epsilon naught E square. This is final result. Correct? So what is the energy density for the parallel plate capacitor? It is half epsilon naught E square. So keep this result in your mind, everyone. Note down. Now let's read one question on the basis of this concept. So what is the question we have? In a parallel plate capacitor, the distance between the plate is d, potential difference across the plate is V, energy stored per unit volume between the plate of the capacitor is what? So here we want energy stored per unit volume, means we have required here energy density. Correct? We are looking for the energy density. So we are looking for the energy density, and energy density formula already we knows, it is half epsilon naught E square. But if we will see it here options, so in the options we have different form, correct? So think it, everyone, which one is correct, simplify and put your answer in the comment box. Correct? So do it this question from yourself, and I am giving you this question in a homework, and put your answer in the comment box, everyone. So note down, everyone. Now let's see next topic, spherical capacitor. So here we want capacitance of this spherical capacitor. So how we can find? Let's see it, everyone. So this is first point and this is second, correct? First point is present on the surface of the first sphere, and second point is present on the surface of the second sphere, correct? So potential at this first point is, let's suppose V1, and the potential at this second point is V2. So what is the V1 value, everyone? V1 is, correct, on the first sphere we have plus Q charge, and on the second sphere we have minus Q charge, correct? So V1 can be written as what? K Q by A, and due to this minus Q charge, potential at first point can be written as, because this is negative charge, that's why potential is negative, so we will put here negative sign. So it is minus KQ by B, correct? This first point is present inside the second sphere, correct? So that's why we are writing here KQ by B. Now we will write V2. V2 equal to what, everyone? V2 equal to KQ by, and here first of all I am writing due to this plus Q charge. So potential due to this plus Q charge at second point can be written as KQ by B, and due to this minus Q charge, potential at second point is minus KQ by B, correct? So now we have V1 and V2 value. So what is the potential difference? It is V1 minus V2. So if we will subtract this V1 and V2, so we can see it one thing here, KQ by B is present here and KQ by B is present in the second term also. So when we will subtract this both, then this minus KQ by B will get cancelled out. Then remaining term we have KQ by A minus KQ by B, correct? Now next is what? Take KQ is common, and we have 1 by A minus 1 by B, and this is potential difference. All right. Now the next thing is what here? We want a capacitance. So according to the definition of capacitance, capacitance can be written as Q by del V. So what is the value of del V? It is K Q 1 by A minus 1 by B. Here Q is cancelling, correct? And the K is Coulomb constant here, and the value of K is what? It is 1 upon 4 pi epsilon naught. So finally, after simplification, we will get 4 pi epsilon naught in numerator, and if we will simplify this 1 by A minus 1 by B, then we will get AB by B minus A. So this is the capacitance, everyone. And what is the potential difference for this spherical capacitance? It is KQ 1 by A minus 1 by B. Note down, everyone. Let's see it one question on the basis of spherical capacitor. See it what question we have. Calculate the capacitance of a spherical capacitor consisting of two concentric spheres of radius 0.2 meter and 0.6 meter. The material in a space between the two spheres is vacuum. So between these two sphere, vacuum is present, correct? And we want capacitance. Okay, so let's see how we can do this question, everyone. So what is the A value here? A is 0.2 meter. What is B? B is 0.6 meter, correct? So we want a capacitance. Capacitance can be written as 4 pi epsilon naught AB by B minus A, correct? So 4 pi epsilon naught value is what it is, 8.85 into 10 raised to minus 12. A is how much? It is 0.2 and B is 0.6 divided by B minus A. B is 0.6 minus 0.2, correct? Now simplify this and you will get the capacitance after simplification. Correct? So very easy question, just formula based. If you know the formula, then easily you can simplify this question. Note down, everyone. Let's see it next slide, everyone. Now we will discuss about the cylindrical capacitor. So here we want capacitance of this cylindrical capacitor. So how we will get, let's see it, everyone. So if you want the capacitance, so what we can do it according to the definition of the capacitance, capacitance can be written as Q by del V, correct? Means we want here potential difference between these two surfaces. Once we will get this potential difference, correct, and this potential difference, if charge we will divide with this potential difference, then we will get the capacitance. So here what we want potential difference, correct? And potential difference is depending on the electric field. So we need to find out first of all here electric field also. Once we will get the electric field, then we will get potential difference between these two surfaces. So let's see it how we will get this electric field. Okay, so see it. The central axis. This is R1, inner cylinder radius, and this is R2, outer cylinder radius, correct? R1 and R2. Okay, and let's suppose here we have plus Q charge and here we have minus Q charge. We want electric field between these two surfaces. So what I will do it here, I will apply Gauss law, correct? So at this P point I want, this P point is present at R distance from the axis. So at this P point we want, so what I will do it here, I will apply Gauss law. So let's see it, everyone. So first of all, we need to consider one closed surface. So this is closed surface, everyone. Now apply Gauss law. What is the Gauss law? Closed integration E dot ds equal to Q in by epsilon naught. Correct? What is the Q in? How much charge is present inside this closed surface? It is Q. Correct? Between this E and ds we have dot product L. So if we will remove this dot product, then we have cos theta. Cos theta is the angle between electric field and area vector. So here we have this cylinder, everyone. So this is the direction of electric field and ds also present in the same direction. So angle between E and ds is how much? It is 0 and cos 0 value is 1. So if we will remove the dot product, then we will get cos 0, which is 1. So easily remove this dot product sign and E is constant. That's why I put E outside the integration. So inside the integration we have only ds. Alright. If I will do it close integration of this ds is what? It is the element present on this curved path, correct? On the curved surface. So if I will add this all small element which is present on this curved path, So it is equal to surface area of the cylinder, which is 2 pi RL. Let's suppose length of the cylinder is L, everyone. So what is the surface area of the cylinder? It is E equal to E into 2 pi RL. So 2 pi RL is what? It is the surface area of the cylinder. Okay, equal to Q by epsilon naught. Now E equal to Q by 2 pi R L epsilon naught. This thing we will get. So what we are getting, electric field is equal to Q by 2 pi R L epsilon naught. So this is the electric field at R distance. Here this electric field is not constant. We can see it here. Here electric field is a function of R and R is varying here, correct? So between the electric field and position we have hyperbolic relation and electric field is not constant. So if you want a potential difference, so we need to find out first of all potential difference for the small region. So let's see it now. Next, what I will do it here. Now what I will do it, I will consider one small region in between these two surfaces, and distance of this region from the central axis is R, and thickness of this region is dr, correct? And in this region I am considering electric field is constant because this region is very small, that's why I am considering. Okay, so change in potential for this small region can be written as dB equal to ER dr, correct? This is change in potential for this small region. We want between inner surface and outer surface. We want potential difference between inner and outer surface. So we need to integrate here. So we will integrate on both sides, and now we need to put limit also. So think it, what should be the limit, everyone? Integration of dB is what is the del V, and ER value already we have, we got it. It is what? It is Q by 2 pi R L epsilon naught. Q by 2 pi R L epsilon naught, correct? Dr. This thing we will get. Okay. And what is the limit of integration? R1 to R2. All right. Now integrate. Q by 2 pi L epsilon naught is constant, so put outside the integration. And inside the integration we have R1 and R2. Inside the integration we have 1 by R, and limit is what? R1 and R2. Now integration of 1 by R is what? It is log R, correct? So del B Q by 2 pi L epsilon naught. 1 by R integration we knows it is log R, and then put limit R1 to R2. So we will get log R2 minus log R1, correct? And this thing can be written as del B equal to Q by 2 pi L epsilon naught log R2 by R1. Correct? Here we are using log property when we have log A minus log B, so it can be written log A by B, correct? So now we got it, potential difference between these two surfaces. So this thing we got it. Now we have potential difference between these two surfaces. We want a capacitance. So what is the capacitance? According to definition of capacitance, C equal to Q by del V, correct? So what is the value of Q? Q is Q. What is del V? Del V we got it Q by 2 pi L epsilon naught log R2 by R1. This thing we are getting. Now Q is cancelling, then finally we have capacitance is equal to 2 pi L epsilon naught by log R2 by R1. Finally we have this result, correct? So this is the capacitance, everyone. So if we have a cylindrical capacitor, then the capacitance is 2 pi L epsilon naught log R2 by R1. So keep this result in your mind, everyone. It is important. And we have potential difference also, which is Q by 2 pi L epsilon naught log R2 by R1. Note down everyone.